Hi, everyone, and welcome back for the session. Today, we'll be finishing up on Voyager, which is using large language models to plan for an agent to execute tasks in Minecraft. And we'll be discussing an even more interesting paper called Goals in the Minecraft. Let me just show you the paper title, where they also do a similar large language model approach, but the way they prompt the model and the way they decompose the tasks is slightly different, but this achieves much better results. So we'll be analyzing why so. All right, so let's begin by covering what we recap what we had last week. So last week we did Voyager, and Voyager structure is comprising of three main parts. Okay, the first part is the curriculum, whereby a large language model will be given what task has been succeeded, what task has failed for the particular student, and it will then come up with the next task out of a list of tasks. What's the next task to give the student? All right, so once the task is given, the student then needs to come up with some code, which will be given to the MindFlayer API. All right, this is actually kind of a bot agent using the MindFlayer API that basically takes in observation inputs from the environment, and then using this bot, they will basically describe some condition, what will you do if certain condition, then you do this, and so on. Using this, generate some code. This code will be used as the action for the agent, and then see whether it works. If it doesn't work, the error messages as well as the environment feedback messages would be given again to the student so that he can give he or it can give better code. And if the code succeeds, the code will then be used as a new skill. So this entire code, like for example, combat zombie, if it works, it will be created here that could be used next time. So every time there's a skill that needs to be done, this will basically will retrieve the top 5 neighbors based on semantic similarity to the task at hand. Top 5 neighbors from the skill library will be used. So this part here, whenever we come up with a new task, typically in the training step, there's no decomposition, but when we do inference of new tasks, this task will be prompted by GPT to be split into subtasks. Okay, although this is not really done very explicitly and very in a desired format, like what Goals in the Minecraft does. So Goals in the Minecraft, they actually did this part better, in my opinion. They decompose the subtasks better from the main task. All right, and the thing is, this decomposition is actually quite important for Minecraft because a lot of items come from a certain order. Like for example, you need wood, then you go to stone, then maybe you go to diamond. There's an order that you need to follow. So there are certain areas of improvement that I think could be improved on Voyager. So let's just begin with, before I move on, any clarifications here? Because this is just a recap of what I've covered last week. Okay, let's move on. So the conclusion of what we see is that using large language models like GPT is actually quite good at learning zero-shot a new environment. Or if it's really too difficult, you can give it some examples. Like inside of the prompts for the student and for the teacher in the previous slide, there's some examples of what are good outcomes or what are good reference materials to use. So you could use this to do conditioning of the generation. I have tried this on the ARC challenge, the abstraction and reasoning corpus. If you do few short example prompting, GPT is better able to understand what you want because sometimes the domain is not exactly very common. All right. But for Minecraft, actually, there's a lot of data online. So GPT itself already has some baseline knowledge of Minecraft. All right. So if we can imbue it further with in-game context, because GPT doesn't have the game state. So if you can imbue it with inventory, player biome, enemies nearby, this can help the GPT generate better action plans. So this feedback loop is quite important. And this feedback loop is very similar to React, where you have thoughts, observation, action. Thought, action, observation. So whatever you see from the game environment, the observation, okay, this will actually be fed back to the planner again, so that it can do the same process as well. So I would say this is just a variance of this observation part from the environment conditioning on the code, and you can repeat this whole process. So this is very important because without this kind of feedback loop, your code will exist in a vacuum, like the GPT will exist in a vacuum. You kind of need the GPT to be like sort of embodied as much as possible in the environment, and this feedback helps to ground it. Right? External memory has shown to be quite important, especially in this case. You can learn increasing complex skills by composing more and more like fundamental skills into larger and more complex skills. Okay, so this is something that I like. If there's any takeaway from Voyager, the takeaway that I have is that a curriculum helps. Okay, you need to go from the easy task to the more advanced tasks, similar for how humans learn. And a skill library helps because once you have memorized certain stuff, like for example, walking, running, for humans, I mean, walking, running, drinking, you don't want to keep learning how to do them. You already want to know how to do it. So this is called like repeating actions from memory. So it's very efficient. Of course, this is the slow method because it relies on memory. Okay, eventually, this should be encoded in muscle memory, or basically like your fast neural network. So this ideally should be done like in both slow and fast. I mean, my fast and slow framework. But in this case, we cannot really do the fast because we do not have the weights that we can learn, because the GPT weights are not trainable at the moment. Okay, but if you could train them, it can actually be trained to give you more and more accurate outputs based on the task at hand. So that's the kind of muscle memory I'm talking about here. All right. Oh, but what's wrong with this paper? Okay, there's a few issues that I've identified. I feel like there's too much, like too many prompts are too specific to Minecraft. Like the examples they generate, all this are like the few short examples to prompt the agent what code to generate. All this, like they already said that, oh, pigs are above ground, diamonds are below ground. All right, so all this require a lot of hand tuning. And if you want to go beyond Minecraft, it's not obvious how you do this. I mean, the more obvious method is that you could retrieve like some like data and then generate these examples. Yeah, that will be better. Yeah, you could do some form of retrieval augmentation, retrieval augmented generation. Right, you can do it on another domain just by having like a database of what's good in this domain. Like maybe if you're talking about Arc Challenge, you can give like a description of all the possible stuff in the Arc Challenge. Maybe you can come up with prompts to help you do it. Yeah, so this is something that I think could be done better. All right, agent does not start from scratch. Okay, there's some basic movements already embedded. Movements, should, all these are already embedded inside the API as the basic functions. Okay, so this one, one way to learn it is maybe you can use some form of like decision transformers. This is like a baseline like RL level, RL. Okay, it's not really RL, it's more like large language models predicting actions, using action prediction to drive behavior. Like you learn what's the state and the action mappings using action prediction. Yeah, so this maybe can help at a lower level. All right. So there's another way to do this, and it's what we mentioned last week, which is if you could give, instead of the fundamental actions like movement, you could give like even more basic actions, like even more basic actions. Like for example, move forward, shift angle to left or something like that. Yeah, so you can do like very, very basic mouse and keypad actions. And you can then compose these mouse and keypad actions into like the primitive functions that we see, like move, shoot. Yeah, so you can do this step here using large language models. Okay, you might be able to do like what the decision transformer is doing. So this part, I'm not too sure whether it's viable, but I think this is some possibility that we can consider, like using the semantic meaning of basic actions to try to chain together, like how to walk maybe. I mean, you think about it, like for example, if you know that moving your left leg forward and moving your right leg forward are two different actions, and then I tell you to walk, can you, from the semantic meaning of walk, deduce that you need to move your left leg forward and then your right leg forward? I don't know. Any opinions? Do you think we can do this for basic movements to learn using text-based semantics? Okay, so take it as no, okay, because I would like to say the answer is no. Yeah, Sam says probably not. Yeah, so I think this part here still requires a bit of try and error. So you cannot run away from doing that at this very basic level, because the actions may not carry semantic meaning, unlike the higher levels. All right, so they're very smart here in this paper, because by avoiding this basic level mapping, you actually avoid a lot of problems of large language models. I mean, that's not really a problem. It's just more like not the best domain specific stuff that you could do with it. Okay, so the last thing that the paper mentioned is that they said that they can, because right now the agent has no vision. The agent just receives text-based information from this function called bot.chats, which like describes the environment to the agent. So what the agent could possibly do is to have visual models to augment some information about what it sees to the agent. Okay, but I don't think this is a good idea, because image models, they have a lot of high dimensionality input, and this input comes in the form of like red, green, blue, and basically people have found it very difficult to like even try to understand what's images. Like you look at ImageNet, in order to understand what's going on, you need to use like a ResNet. I mean, people have tried to use vision transformers, but that really just overfits on a lot of data. Yeah, I don't like vision transformers. One day I'll do a session on it. Yeah. So this is why like vision models right now too high dimensional. In order to like retrieve out a slice of information from the very complex vision domain requires a bit of skill. Okay, you need to know what you're looking for. So like sometimes maybe you might want to do like vision question answering, like given an image, all right, given an image, you ask it a question, okay, using some model like that. So you have a question that is like based on your task at hand. Maybe you want to ask like, what is my inventory? Then this can come up with the answer. Okay, so something like that will be for generic environments if our image to text models are advanced enough. And you can process the output of this in text, which is great. Okay, because trust me, you do not want to be processing things in the pixel domain. Okay, that's, if you have ever done work in the pixel domain, this is going to be very complicated. Okay, but for the game like Minecraft, okay, we actually have even better ways to do it than vision question answer. We can do it using stuff like LiDARs, where you can just like use where the ray passes from the player lands on to get information from the game. So this is if you have access to the game simulator. So for those who don't know what's a LiDAR, it's like a laser device. So let's say for this example, this is the player. Okay, this is the game object. The LiDAR enables you to form a ray, and then wherever the ray hits, okay, this object can be fed back, the information can be fed back to the player. So this LiDAR thing is, it can already help to like simulate vision, because if you put multiple LiDAR rays, you already know, okay, what blocks am I encountering? And in Minecraft, because everything is blocks, it's quite easy to know. Okay, I mean, it's a 3D environment, but you already know what blocks you encounter. So this might help to significantly reduce the complexity of the 3D domain. So stuff like that could be possible in Minecraft. Okay, but in general, if you want to do for like real world domains, maybe you need to do some question answer to images. Okay, this is still open for discussion, of course. Right, let's move on. So these are some potential improvements. I think one way is to have like multiple agents, and then you could perhaps learn from each other, learn from the best performing agent, so that your, like for example, your skill library can be updated in that way. If not, what will happen is that if you only have like maybe one agent, sometimes it may get stuck. All right, so another way is we can also learn from expert trajectories from trained experts. That is something like behavioral cloning. Like you can learn action sequences, or in this case, you can learn code that is already quite reliable. All right, so the model answer is very important. Okay, and this part, I think is one of the issues of this Voyager, is that it uses code. All right, so if you use code like that, like you need to have the exact code sequence working perfectly. So GPT-4 is not that great at generating novel code. I mean, it's great to a limited extent. If your code is too novel, it's very difficult for it to generate properly. So this is one thing that I think could be improved. Okay, in addition to like learning from trajectories. For the action space, I think they are lacking some form of prompting from broad to specific actions. because like you can say that, oh, what's the broad action you want to take first, then you narrow down to the specific actions that you want to do. So this could potentially help it to like, okay, maybe I need to craft a stone hammer first, then from stone hammer, then I need to craft like wood hammer. So something like this could help it to do very, very like, it's something like hierarchical planning. Maybe this should be done like, maybe can be done at the planner level, at the task decomposition level. Okay, so you will see later in Ghosts in the Minecraft where they did this, right? I quite like the paper for Ghosts in the Minecraft because they did something like this as well, right? And this last point is about like world models, because the critic currently just evaluates like whether or not the task is met. Okay, but it may not like help to evaluate whether the code runs. So this one is a question mark, okay, because you know world models are inefficient to train, but if you can have something like a world model that can help to evaluate whether this code will work or not, this can be very valuable feedback given to the planner. So this part comes in over here. So if your verification step can also give you a feedback here, this would help greatly in terms of knowing whether your code will run or not. Yeah, so this is a optional thing, only suitable if you have a world model. Okay, if you don't have a world model, then don't bother about this part, because learning the world model is very difficult. Okay, and that's all for Voyager. Anything you want to add to the critique of my critique of Voyager? Anyone? Okay, if not, let's move on, because I do want to have the discussion session at the end. All right, so Ghosts in the Minecraft. I really like this paper a lot, because this paper, it's actually, in my opinion, superior to the Voyager paper. Okay, although they did not release it open source, but the way they did the breakdown of the tasks is really quite intuitive, and I really like it a lot. So let's see what they did. So let's just start with the results first, all right? So the results for Ghosts in the Minecraft is that out of like the selected 200 over items by the researchers, okay, those items don't need some special quest or don't need some like special unlock, all right? So these craftable items can be done like straight away from your start state. You just go and gather materials and you can craft them. You can see the existing Minecraft agents are those in red, okay? These are what existing agents could unlock, okay? And you can see that they unlock everything. So the green color is whatever they can unlock. So they basically unlock the entire skill tree. So unlock the entire craftable items tree. So this is quite an achievement in my opinion, because this means that they can translate the wiki into actions. Because actually all this is all available in the Minecraft wiki. But in order to translate it into game actions requires some form of interfacing. So they did the interfacing right. Okay, you look at Voyager, they also have the Minecraft wiki, but they are unable to craft all the items. So this alone can already show you like, okay, provided that they are not fabricating the results, this shows that the Ghosts in the Minecraft paper is actually superior to Voyager. Right, so we can take a look at like comparisons to reinforcement learning methods. So this is the vision pre-trained transformer, if I'm not wrong. Vision pre-training. Okay, this is by DeepMind, using videos of people playing Minecraft coupled with the mouse and the keyboard actions. So they hired people to do that. They learn from that video, and then this actually achieved quite good training results. Okay, but for example, to get the diamond ore, okay, they said they did like 20,000 over hours of training. So this is not very viable with like, if you use video pre-training, imagine the amount of data you need to do this. All right, so just learning from human actions and the simulated trajectories from video alone is a very inefficient way to do learning. Okay, because it requires just too much videos to do it. Okay, this is the other DEPS. I think it's describe, explain, plan, select. So they actually use a similar planner and a similar like agent executor to like this LLM-based methods. The only difference is that the executor is not code. Okay, it's not like actions interface in the API. The executor here, the selector, select an RL-based actor. So the actor is still like given a goal, do the task. So it's a goal condition RL method here as the controller. So they call it the controller at the end when you select the controller. So you can see that the results aren't that great. Okay, although in the paper, actually this part here, there's a discrepancy. This is from their GitHub. But in the paper, they put something like 100, 100. I think the results are like towards 100, and here's like 80 or something. You can see the paper again. So this part here, I'm not too sure like which is the correct results, because there's a discrepancy between their paper and the GitHub. But I would assume that it can't be 0, because like this describe, explain, plan, select, I'm very sure it can craft a wooden tool. It's quite easy to craft this. So I think it's good, but it should be slightly inferior to the VPT model, right? But the main thing is, okay, maybe this is the results that they show is over here. Yeah, maybe this is the results. Yeah, but I remember there's 100 somewhere. Yeah. So the main thing is that if you look at the LLM planner with goal decomposition and with structured actions, okay, this actually achieves very good results, even better than the video pre-training. So this means that without extensive video knowledge, okay, but of course there's a difference here. This video pre-training doesn't have the wiki. So this Minecraft wiki is already given to the planner. So there's some domain knowledge here. So this video pre-training doesn't really need it. You just need the video and the action sequences. Like, yeah. So this shows that if we have the available knowledge, and if we can decompose our goals and we can apply structured actions. So what is structured actions? Later I will explain to you. So structured actions, basically it means actions that are fundamental and cannot be changed. All right. So these are like the primitive functions. All right. So if you have this given, all right, this actually improves the solve rate by a lot. Yeah. I mean, if you look at here, without the structured action, it doesn't solve. Okay. So again, this one here is a bit like weird, because they have this on their GitHub, but they don't have it in the paper. But I like this table a lot more. So the main thing that you can take away from this table is that the LLM planner, if infused with the right structure, can beat traditional RL methods by a lot. Yeah, that's the main takeaway. Okay, so this is the thing that I thought was quite cool. So Dreamer v3 is a model by DeepMind, I believe, and this basically takes billions of steps to learn. You see, like billions, literally billions of steps. Okay, if you use this model that they have, all right, this goes in the Minecraft. You just need a CPU, and then you can learn it like this is the number of environment steps it runs. Okay, so you can learn it within like 10,000 steps. Okay, but even before that, like just at the beginning, you can see that it's already like 30–40% success rate just using semantic knowledge alone. Right? This is very important, because this means that if you can encode your environment problem in terms of text-based semantic knowledge, you don't need RL to solve it. You can just do pattern matching with the semantics. And this is a new paradigm that I think is very important, because it can enable zero-shot learning. Right? So you can see this is the models that they have that use like reinforcement learning based methods. You can see the difference yourself. Yeah. So there's no need to emphasize this. Yeah, I just want to bring home the point that RL methods are bad. All right. They are probably not going to survive the next few years. Yeah, I think we will need to infuse some form of large language model learning. And maybe at the fundamental level, the baseline level where text-based knowledge cannot really help, then you could have like RL, maybe in the form of like decision transformers. Okay, it's not really RL, but like also transformers, but in a next action prediction format. Next action prediction is very important. Yeah, so you said your time has come. Yeah. I always believe RL is not good. Yeah, but I've been researching on RL for the past 3 years, and I've been trying to find alternatives to RL. And yeah, this really just shows that there are alternatives right now. And if you can do the planning at a much higher level, the LLM is a very viable alternative. Next. Okay, so this is something quite interesting also. They are able to construct the Netter portal without human feedback. So this alone is really better than Voyager. But you know what's the most important? Because they don't use code generation, they use a list of actions to denote their action space. ChatGPT can solve this environment already. Yeah, so this is really, really quite cool. ChatGPT can construct all items. Okay, if I read that paper correctly, ChatGPT can do it already. So it just points to me that maybe we shouldn't be using. Sorry, I see what happened. Grant access to. No, someone wanted to control my computer. Okay, yeah, but I just put no. All right, so let's move on. The ChatGPT interface can already be used to get the performance in this paper, which is really very cool because the Voyager paper used GPT-4. So let's see. Okay, I hope I've excited you all enough. Okay, let's see how they did it. Okay, so this is the normal reinforcement learning method. You maybe give it a goal, okay, or rewards. Okay, we can phrase it in a goal as well. Okay, the RL agent will then like do the actions like move using keyboard and mouse, and the environment will give you back the observation to the agent, and then you keep doing this loop until you succeed. Okay, but this is actually quite tough to do for very, very long scale actions. Okay, imagine if I want you to craft like diamond X. You kind of need to do the same fundamental actions like walk, mine, walk, mine. You need to do this like maybe 10,000 times. Can you imagine that, you know, you need to have a 10,000 steps of actions first before you get your reward? That's why reinforcement learning methods suck. Okay, it takes too long a horizon. Okay, it's very good if the horizon is very small, but if the horizon is like huge, you will take forever and you may not even get your reward. Okay, in contrast, okay, we can break down this keyboard mouse actions, okay, into fundamental actions that you need to do. Like, for example, explore the area, mine the area, craft something. All right, if you can break it down like that. So for each action, like explore, it could be like a series of walk, but it's instead of times 100, maybe it's times 10. Yeah, so it's much, it's really broken down into chunks. And like over here, they already use like some form of A-star search, like chessboard. They call it chessboard search, where like basically if you want to find an item, find item by going through all areas iteratively. So they already did something like that to encode it inside here in the explore part, so you will never get lost, right? So this is a bit cheating, but I mean, if we are looking at the high level planner kind of thing, it's fine, okay, because it means that if you already have a very efficient navigation system, you can't pre-build with it, maybe, okay, you can then focus your efforts on this part here, this high level part here. So this part actually is very similar to Voyager, so I'm not going to go through too much. You take a goal, you compose to sub goals, okay, and then you have a planner, and then you have feedback, and then you keep going on. The only thing different here is that the action is in the form of an action list, okay, rather than using a code to do in a bot. The action list will be like, you take these actions here, like dig down, explore, you put like your function inputs here, and then you have a list of executable functions. And all the bot just needs to do is to just run this list of functions one by one. And this can craft all items already. Amazing. I'm actually trying to do something like that for my ARC challenge right now. All right. So GPT sucks at generating code for novel situations. But what if you give it the functional primitives and ask it to choose what primitives it could use? Apparently this works. So I think this is quite interesting. All right. Questions here? Okay, let's move on. So the main thing, if you look into details, okay, is that they first have a decomposer. Okay, this decomposer has this object count material to info, which I'll go through later. This will basically split the main goal into sub goals of this format as well. Okay, and then you keep splitting until you reach an action. Okay, because action is basically like something that you cannot split anymore. All right, so this is the decomposer. Okay, after that, when you have the goal, you go to the planner. The planner will take a few functional primitives here, and then you will choose from these functional primitives what function to apply and to what target, you know, because these functions actually need to take in some parameters. And then this will have a list of actions executed by the environment, and then you'll get feedback. Okay, of course, there's memory as well. So if the task has already been done before, why reinvent the wheel, right? Just use memory and just perform the same list of actions. So I really like this part because it reminds me of my fast and slow. This actually I really like this paper a lot. I mean, if I will ever do a paper on Minecraft, I will do something similar. Yeah. So this is really a nice paper. Yeah, you should go and take a look at this. All right. So the next is the LLM interface. if it basically just executes these actions here in the action list, okay, and it proceeds to interact with the environment by processing the raw information. So in this case, the raw information is keyboard mouse input. Right, raw observations, it receives back the LiDAR inputs, it receives back the information of the biome and so on. So this part here, because it's not open source, I'm unable to see exactly how this is done. But they say that it's similar to the Mind Dojo paper, the observations and the keyboard mouse input actions. So I would say that in terms of like low-level interfacing, it does still go to the low-level interface, but there's some wrapper here. There's some API here that wraps it. Okay. Because the API is all encoded by this explore Minecraft dig down functions, which I cannot see right now. Okay, so because it's not open source. This part here, I think it's quite cool if they could map it directly to the raw observations and do this API, because this means that as long as, so this part here, the thing is this is not learned. This is not learned. This is human given. Okay. So this is the drawback right now, is human given. Okay, but if we just focus our thinking in the high level realm, it's actually quite impressive, because just given these functional primitives, I can solve any problem. That's cool. Okay, I mean, you can treat this Minecraft problem as like that. You have a list of tasks to achieve. Each task can be broken down into subtasks based on Minecraft wiki, because Minecraft wiki actually got all the answers. Okay, and then what you want, here are a list of functions that can help you. Give me the functions in a list format, something like that. Yeah, so you can basically use the large language model to map the knowledge given from the from the Minecraft wiki, and you basically get a list of actions that are already conditioned on this environment. So they're using LLMs correctly. You are able to do attentional-based mapping, or you can map relations between the input to output. In this case, the input is some list of tasks you need to do, and you already know the steps that you need to take. Then you just need to map to the functions that can enable you to achieve those steps. Okay, so some people might say it's cheating. I think the path mentioned last week that like if you have the wiki stuff of like how to craft stuff, then the game is like quite easy, because you can just execute the you can just basically follow the guide. Okay, I agree, it's quite easy, but right now existing methods can't really do it yet. This is the first method I've seen that can just translate the wiki directly into actions. So I think this is still quite cool. Okay, future work, probably you might want to remove the Minecraft wiki and learn from scratch. Okay, read, or you can construct the wiki through exploration. That'll be interesting. Yeah, if you can construct knowledge database from exploration. Okay, but now we are given that we have the entire human knowledge base. How do you translate that into action? And this GITM goes in the Minecraft is able to do it. I think that's impressive. Yeah. All right, so let's see. Sorry, I talked too long on this, okay, because I really quite like this structure. All right, so this is the detailed structure for the planner. So this is actually this part here. So just focus your attention on how the planner does it. So let's take a look at the planner. So the planner, what it does is that it takes in some interface from the this is basically the list of primitives that you can do. Like you can explore and what are the kind of inputs that it takes. So all these are described in detail to the planner. All right. And then what will happen is that we will need to we need to achieve like a query, which is a goal. So this goal is quite cool. You just need to find out this is the task you need. And actually they have a very nice prompt format. All right. Their prompt engineering is top-notch in this paper. Okay. They have this prompt format called external info, where it gives you the goal and then straight away tells you like, okay, where can this goal be done? Right? It's like telling you the answers, like what is 5 + 5? And say addition is typically, then this is like the hint. Addition is typically done by taking number 1 and adding the second number in this format. Yeah, so this helps to, like, because of this, it helps to condition like how the actions are done. All right, so there's also feedback from the environment. So the environment, if there's an error or what, they will tell you in this format. There's also a reference plan. Okay, so what's a reference plan? A reference plan is if you have past examples of success, in this case, like if you already have done a diamond before, you can give the list of actions that these are the list of actions like dig down, explore, approach, mine. So by executing these 4 functions in this sequential order, you can get diamond. So you can just basically, if the memory is populated, you don't even need to like come up with anything. You can just copy paste the memory and use it. Unless there's some problem, then you need to refine it. But this memory is cool. I like it a lot because it enables action reuse. Whatever successful action list that you have come up with in the past, you can just use it again. Okay, so the response format is also very cool. You look at this response format. Okay, so first you explain your action failure, or you explain what you want to do. Thoughts, you can explain like what basically how do you think the plan can work. You basically break down your plan. Okay, and then the action list. So I mean, if I were them, I wouldn't have caught this thoughts. I would have caught this like detailed steps. Yeah, because like it helps the model prompt better, I guess. Yeah. So what happens is like, okay, the last action failed because this cannot be found. Okay, so what do I do next? I need to dig down to level 12, explore diamond ore underground. Okay, and then mine it with the tool. So this directly translates into the domain specific action list. Okay, I really find this very cool because this is exactly what I'm doing for ARC. Yeah, next week I think I can share a bit of what I'm doing for the ARC challenge. Yeah, so it's very, very similar to this whole process. I did this process, it like doubled the success rate of ARC challenge with this feedback loop. So that's cool. That's cool. Very, very, very cool. So this idea works. Okay, this really works. Okay, no joke. I like this idea. All right. So how do they do subgoal decomposition? So subgoal decomposition, remember the format: object, count, material, to info. All right. So this is basically translating the wiki into subgoals. All right. So the wiki itself, the info itself, actually all this, when they give the LLM, they'll give in like what the target object is, the quantity and the name, and the knowledge base. This is cool. Okay, what's this knowledge base? This knowledge base is passage retrieve, okay, from Minecraft wiki that is relevant to the target object. So they already did some form of retrieval augmented generation here by putting the knowledge base inside the prompt of the agent. And then from this knowledge base, the agent is supposed to come up with this thing here. So like wooden pickaxe can be crafted with 3 planks and 2 sticks, and crafting table as the tool. All this came from the wiki. Okay, the agent doesn't need to learn all this. But what's impressive is that by the way they prompt it in this structured manner, which I like a lot. Okay, when you do prompt engineering, you should try to make your prompts as structured as possible. Then it will help to cue the agent to generate stuff. So they start with the object, they start with the number, they start with the material. So this is very, very good prompt engineering, because if let's say if your count is 2, right? Then because you know this is 2 and this is 3 and 2, your info over here can be updated. 2 wooden pickaxe can be crafted with 6 planks and 4 sticks. Yeah, so if you did this the other way, right? Like you put info first, you cannot rely on the sequential prompt engineering structure here to get your info. Okay, because actually what they really, really want here is the info. Because this object count material to info is just a way to sequence the prompt such that the most detailed information goes out at the info. Yeah, so this is prompt engineering at its finest. We take the Andrew Ng course on prompt engineering. I don't think they teach, I mean, they teach something like similar. They teach some sequential prompting, but I call this sequential prompting. And I think this works very, very well. Yeah, try it out. You prompt it in a sequential order where the last part relies on the first few parts. The last part will be generated very nicely. All right, if you can do this kind of method of prompting. Okay, so this is a great structure. And I think this is like maybe 50% of the reason why this is better than Voyager. Okay, because their prompts are better. Okay, if you look at the Voyager prompts, they are not as great as the goals in the Minecraft prompts. So if you ask me to rate the prompts, I rate the goals in the Minecraft as like 9/10 or 10/10. The Voyager prompts maybe about 6/10. Okay. And yeah, this is very, very similar to how I were prompted as well. So I like this paper a lot. All right, so next, how do we get the action primitives? So earlier on, remember we have the list of stuff like dig down, go up, build, craft. Okay. All this did not come from thin air, all right? They actually have a very structured process to generate the action primitives. So they actually asked the large language model to do a 3 structured action planning. So there's 3 1 4 1 tasks in Mind Dojo. MindDojo is like a Minecraft environment where they split the Minecraft environment into different tasks, like to mine for diamond ores, to fight Slender Man. You know, there's different explore Nether portal. All these are predefined tasks already, and these tasks have a predefined like way to win. All right. So what will happen is that the prompt will convert each task into like a series of actions, okay, that involves this verb, object, tool, material, okay, and this will then be refined, okay, into a structured action. Into a list of like fundamental actions, which will then be crafted into structured actions using like some form of chunking, like you group together the most frequent actions, or you merge together actions with similar functionalities. Okay. Unfortunately, I'm not able to give you more insight in this because the paper didn't explain this that much, and the code is not open source. So I can only give you some information of this from the appendix, because I find this very cool, because this can apply to any environment. If we can have a list of tasks that are like the baselines, you could potentially use this method to generate your functions primitives that could work for any environment. All right, so let's take a look at how this can be done. So this is how they actually did the like from a goal, all right, generate out into specific actions. So they actually asked it to label like 1, 1.1, 1.2, 2. So in order to achieve 1, you do a sub action 1.1 and sub action 1.2. So this way is to prompt the LLM to do broad goals and specific goals. Okay, the alternate prompt for this will be to generate broad goals, broad action plan, and then after that, second is generate detailed action plan based on the broad plans. This should be basic actions. Yeah, so something like that. So you could do it like that. You don't have to do it in this way of prompting. Okay, so I have done prompts like this, like broad and detailed, and it works perfectly fine. So this is quite cool, because what it does is that for any generic goal that they have, and this is from the predefined 3141 task, you can generate a list of actions at the bottom. You can generate a list of basic actions. And from these basic actions, what do they do next? Okay, what do they do next? They convert each action into a domain-specific action. So this basic action here is from a sentence, all right? And this sentence comes from the previous table, you know, where you have the broad and specific. This is the specific actions. Okay, and then now what I need to do is I need to generate into in the list of actions. So like verb could be explore, object could be like nether portal, tools, maybe it's like armor plate, material is like, if you, let's say, you need to craft iron pickaxe, you need to have iron, you need to have wood, and so on. Yeah, so sometimes you don't need material. So this verb, object, tool, material is like a generic, I would call this, I guess, primitive actions. It's not even primitive action, it's like more like I don't know, it's more baseline action, because I use primitives for the functions. So you can see that this action here, it's still not like in terms of mouse clicks and not in terms of key presses. Okay, so I'm not too sure whether or not they went to that level to map the key presses into the primitive functions. They might just be mapping these baseline actions. Okay, and yeah, which is weird, because, you know, if you look at this, if you look at the start of their paper here, they actually said that it's keyboard and mouse over here. So yeah, it looks like the way they generated the actions doesn't really involve the keyboard and mouse. All right, so it may not be apples to apples comparison with reinforcement learning methods. They might be using like the MindFlayer API also, for all you know. Yeah, because I don't have the code, I cannot comment on how they interface it. But this doesn't look like the most primitive actions to me. Okay, this is still at the higher level of abstraction. Okay. But the fact is, from this higher level of abstraction, like, if they can already generate like this set of structured actions from it, it's very cool, because it means that from stuff like moving, mining, and stuff like that, you can generate functions that could help you achieve these objectives. And these functions, I call it primitive functions, can be then used to plan any task. Okay, so let's see what they did for the action list generation. So this is, I think we can discuss this to see how it compares. Okay, how does this compare to Voyager? Okay, because in this action list generation, okay, this is like your action space. they say that you can only use the actions that I've given you, like equip, move. You cannot generate your own functions. Okay, so in some sense, you have no more learning of primitive actions possible. Okay, you don't need to reference any like skill library because like the skill library is fixed. Okay, I mean, you can still reference the skill library, but you cannot learn the primitive actions anymore because they are all fixed. There's no more move function you can learn. It's always going to be the same fixed move function. But one thing I realized is that if you constrain the fixed functions like that, you don't allow it to generate new functions. Apparently, it can improve performance because like I like Voyager where you can learn your new functions, which I thought was a plus. Okay, this one you cannot learn your new functions, but because your functions are already in some sense like able to map out like all possible task spaces, you don't need to generate them. Okay, but how do we learn to compose actions in a hierarchical way such that you can do more and more complex tasks, right? How can you do that? That is actually done using memory. So later we shall see how they did this. But for the baseline action space, okay, you don't get a chance to learn them anymore. So this might be a downside, okay, because sometimes if the environment changes, you might want to learn it again. But if your environment is more or less fixed, you can constrain it. And I like this part the most, okay? This part is something that we need to discuss in detail later, all right? The reason why Voyager, the other 50% of why Voyager like is not as good as this goes in the Minecraft is that the Voyager code may not run. Okay, but this goes in the Minecraft because it's a list of functions, all right? It's kind of guaranteed that the functions would run. The only thing that could happen is that the functions don't match with the environment. Okay, but in terms of the code structure, you won't have a syntax error. Okay, because like if you follow the function and you follow like what are the arguments here, which are already given as a zero-shot learning in the beginning, they give you the functions and the inputs and the outputs. You can already like sort of guarantee that GPT can generate this effectively. And let me just emphasize this again. This is ChatGPT. ChatGPT can generate this action list already. This is a leap forward because like if you compare to the Voyager, I mean, I use this on Arc as well. If I generate code for Arc, it cannot work for ChatGPT. Voyager uses GPT-4. Goes in the Minecraft uses only ChatGPT. And because of this smart way of constraining the actions, okay, constraining actions, you look at how many actions there are. Okay, so let's take a look at the actions. How many actions are there? You count with me. 1, 2, 3, 4, 5. Let's count my attack as 1, 2, 3. Okay, maybe my attack are the same key. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 actions only. So there's like 9 different building blocks that you can use to make even more complex functions. And this is cool because just with this small set of 9 actions, you can solve everything that is that's required in this crafting task. So do we really need to have open-ended code generation? Think about this because we'll discuss this later. All right. Okay, so a bit of the observation space. So they use like LiDAR arrays, as I mentioned earlier. Okay, they also use voxels with 10 units radius. So this is basically like a bit of cheating. Basically, you have the information of all the blocks around you in a 10 block radius. All right. You also have inventory, life status, agent location. All right. And this basically I use to perform the functions. Like the function, like navigate will need to require all this like information about the blocks around you to find out like where's the nether portal and so on. Yeah, so in some sense it's a bit cheating because when the player plays the Minecraft game, you don't have this voxel information. Like you do have the voxel information, but you need to click on it before you get it. You don't have immediately, oh, around you this is the map. These are the forests, these are the mine blocks and so on. Yeah, you have to sort of visualize it yourself and then you need to decipher, oh, this is a mine block. So there's a bit of visual recognition going on if you play it for real. Okay, here we abstract it away with some stuff like voxels. Yeah. But I mean, if you don't care too much about like how the game is played, okay, it's actually quite amazing already if you could. I mean, there's another pipeline called from vision to getting these voxels. Yeah, this is another pipeline that is missing. Okay, but we start from this pipeline, start from all this basic information. It's already quite impressive in my opinion. Okay. So the training process of how the subgoals action spaces are learned. First, we have the LLM decomposer, generate the subgoal trees. Okay, we have the list of all subgoals. Right, so there's no curriculum planner to choose the easiest action, because the way that they are framing this task is like to generate like they already generated the subgoals, and basically these subgoals are the easier tasks. So what they did is, okay, maybe if I draw out in the tree, it'll be easier. So they have the main goal, they do into subgoals, they do into subgoals. So they already split by hierarchy based on subgoals. And then what they do is learn from bottom first. So they repeat the subgoal 5 times from the bottom of the tree all the way to the top of the tree. They learn 5 times, they get the list of actions needed. So after they do 5 times, they get the successful action sequence, they do summarization. Okay, what this summarization process is like this. So imagine if I have a thing called like find mine wood or mine, I don't know, craft wooden axe or something like that. Yeah. And then maybe the first step, yeah, I don't play Minecraft, so let's say like find wood, move to wood, find wood. So this is action 1. I don't know, maybe someone can tell me the correct steps to craft a wooden axe, but anyway, let's just say that we have like actions 2 to 5 like becoming this. So you can consolidate this whole thing into one action. So you can consolidate this thing into move to wood, find wood. Yeah. So this can basically like help to find out what is the more important actions, what are the more important actions, and what are noise. So eventually, after you like average it out, these are very succinct, very performant actions. And you know, if your environment changes, you can like move to wood, hunt, pick, find wood. I mean, eventually, if your environment changes a bit, you can then consolidate the new changes in the environment, and then this can be updated and summarized into a new like action list. So this is quite cool, because this subgoal consolidation and this like for each subgoal you store the list of actions that you can that you need to solve it. This actually helps to speed up the learning process, because if we look at the next slide, all right, if we look at the next slide, okay, whenever we encounter a subgoal that we do not have experience for, okay, the LLM planner will create a plan without reference. Okay, but once the subgoal is achieved, this action sequence will be stored in memory. And then with prior experience, okay, when we encounter a subgoal with memory, what we do, we'll use the first action sequence as the reference plan. So like, for example, just now, the find or craft wooden axe. Yeah, I apologize to the Minecraft players out there, because I'm just giving a list of actions that I'm not even sure whether it's correct. Move to wood, find wood, or mine wood, something like that. Yeah. Yeah. So do you mine wood? Find wood. Let's say find wood. Okay, so let's say we have an action sequence like that. This can then be used directly as the reference. Okay, remember earlier we have the prompt with the reference in the goals in the Minecraft. Okay, maybe I'll move back to that slide again just to recap. There we go. We have this reference, right? Which is the memory here. If we already have a list of actions that can achieve the subgoal, we can simply output that list of actions into the LLM planner. Okay. And with this reference plan, it's able to maybe just recreate the same reference plan. So, I mean, we don't copy paste wholesale, because the environment might change. We might need this feedback later to condition and get a new plan. But the idea is you don't start from nothing. You start from something. This idea of using memory to help to condition future actions is very important. It's very important. And this is done quite beautifully here, because with this, remember we have skill library in Voyager, which like composes complex tasks out of simpler tasks. Remember we have this. Now we actually have a similar mechanism here. Subgoal memory. From subgoal, get list of actions needed. Can you all see the parallels between this subgoal memory and the skill library of Voyager? Can you all see this? if you can see, you just put a thumbs up. I just want to see like how many of y'all agree that it's similar. Like from a list of actions from a sub-goal, is it the same as composing like a complex task out of simpler tasks? Is there a link here? All right. So I would say yes. Okay, there's a link here because right now the sub-goal is your simpler task. You get a list of actions needed, and then you can basically okay, maybe one action here is like a simple task, and then from a sub-goal you get the list of actions needed. This is like a complex task. And then imagine if this sub-goal goes up to like the higher level goal. So we already solved the sub-goal. We already solved this sub-goal. And then once we reach like this goal over here, actually, no, we won't ever do that. Okay, because the planner will only give you the sub-goals so you will only see this part here. So once we already see the sub-goal and we split into the list of actions already, it is similar to like composing simpler tasks out of complex tasks. And I mean, the complex tasks can be decomposed like that. See, complex tasks. And your decomposer will go into like the base level sub-goal. And this base level sub-goal will then like get the list of actions needed. So this is really very cool because you can decompose your problem all the way into the base level. And at the base level, if you already have done that base level before, like, I mean, if you take an action like drinking water from a cup, if you have done this action before, drinking water from a cup, I drink water in the office, I drink water at my home, it doesn't really matter. You have abstracted this entire list of actions needing to accomplish this goal. You have abstracted this independent of location. So I think this is quite cool because I've been thinking about abstraction also. Could abstraction just simply be running it as a sequence of actions and, like independent of like the state space? Like, because all along in reinforcement learning, we have state space and then we have action condition on the state space. Or what if the abstraction that we really need is just, let's get a list of actions or get something similar. That means like, and these actions can like already interface with your state space natively. Yeah, you don't have to care about, oh, if this state then do this action, this state then do this action. You can just say that, oh, in this particular context, I perform this set of actions. And then like, even though the state space might change or what, the actions can really cater for that. So this is maybe a new paradigm of thinking about like reinforcement learning type problems, state and actions and rewards. Maybe you don't need to map a policies from state to action because traditional reinforcement learning, you have a policy that maps in state to action. Okay, but like maybe you just need to do this, like you just need to do like LLMs. You just need to map context to action or sub-goals to actions. And then these actions take into account the state. So in this case, these are not really basic actions. These are more like dynamic actions. Yeah, so this is a new way of thinking about things because I think it's really much more flexible. It gives you the abstraction space you already need like natively. Yeah, that's good. Let's see the chat. There's a lot of people asking. So you said, but the sub-goals are extracted from the wiki, right? While the skill composition is try and error. So the sub-goals are extracted from wiki through knowledge retrieval, yes. The skill composition by try and error, actually not really. There's no try and error here. The skill composition is just by pattern matching of like given a sub-task or given a sub-goal and given the list of actions and their descriptions, what is the logical like list of actions needed? Oh, okay, for Voyager. For the Voyager part, sub-goals extracted from wiki, skill composition is try and error. The skill composition is, instead of a list of actions, is through code. So I would say that it's very similar to goals in the Minecraft, except one uses a list of actions and one actually uses the bot code, which is like Voyager. So to me, I think asking GPT to create code is a flawed approach because GPT doesn't create code very well for novel situations. I mean, did that answer? Yeah.
That the Voyager paper did not use the Minecraft wiki.
They use. So the Voyager paper in the, maybe let me just show you the part that So let me just zoom to, I have the last week's slides. So the Voyager paper, in terms of the curriculum generator, the memory retrieval is here. So there's a wiki knowledge base that the teacher can use, and this teacher can do the subtask decomposition also. So in terms of subtask decomposition, yes, there's a wiki generator. In terms of like coming up with the task itself like this, you can take a look at the prompt. I think in this case, the prompt here doesn't have the wiki, if I'm not wrong. Yeah, so if you talk about the code generation here, this may not have the wiki. Yeah, but for the task generation here, this has the wiki. Yeah, so you might be right. In terms of Voyager, they may not have the wiki to guide the action generation for the student process.
Sorry, I have another question. So for these goals in Minecraft, do they have something similar to the verification? When you come up with a list of sub goal, how do they test whether it works or not?
Whether the sub goal works, is it? The verification step is not in the sub goal step. So that sub goal is assumed to work.
Sorry, what do you mean assumed to work?
That means for the Subgoal decomposer, like this part here, I did not read any part that says that, oh, they check whether the Subgoal will indeed achieve the goal. So what this means is that it's assumed that the whatever subgoals that come up with can generate back the main goal.
So are you saying before execution, they don't check whether it works or not?
Yeah, I mean, in terms of checking whether it works or not, I guess it's based on whether the agent performs the task.
Okay, then but okay, what happens if it doesn't work?
What happens if the subgoal doesn't work, is it?
Yeah, how does it improve?
Yeah, so once the LLM planner has finished a subgoal, the decomposer will go to the next goal and the next goal and so on. And basically this part here, so the LLM planner will just take in a subgoal and count the actions. But this decomposer here, what they will do, they will basically need to come up with the list of subgoals for the agent to take. And I guess because I don't see a feedback mechanism here, it's kind of assumed that the subgoals will always give you the main goal, I guess, because I don't think they face an issue, because if not, there will be a reflection halfway up to the main decomposer to say, hey, your subgoal doesn't work. Yeah, that's a good point.
But that implies it doesn't even learn, right?
Yeah, I mean, it's more like matching the situation to actions.
And somehow it worked without learning.
I mean, the learning is matching, is to match the task to the action.
Yeah, like you said, there's no feedback. So learning implies you have to at some point, like you can't know everything at the beginning. So when you make mistake, you have to have a feedback mechanism to improve, right?
Correct. So this is not there in the large language model framework. Even Voyager also don't have this mistake, but the main thing is they are trying to match the semantic information present in the wiki to a list of actions.
But Voyager, they have the verification.
Yeah, but for Voyager, the verification will also just be limited to this part here, the planner itself, the subgoal solver. It doesn't verify all the way to the subgoal decomposer or the teacher.
I see. Then okay, can you remind me again the feedback in this part? What does this part do?
Are you talking about this feedback here? This feedback is to take the environment feedback. You can see in the next slide. Environment might give some error message that the function cannot be executed. Then you can use this to ground the agent, because the GPT agent is not grounded in the environment. You can use this to ground the agent such that the generated output will be more suited to the environment. Yeah. So you notice there's one less feedback here compared to Voyager. You know what's the one less feedback? There's no need for code feedback. So it's quite cool, because if you give it as a list of actions, you don't have any syntax errors in your code.
It's just the semantics.
Yeah, it's just a list of actions which is more or less guaranteed to run, because if there's any syntax error in your code, you'll be given here, like the diamond or is too far, like it's not possible. But the code itself, because the code is just given as this here, GPT is able to generate this quite reliably.
You mean given the feedback in natural language form is far, and it can just correct itself by maybe
it can basically map directly what it wants to do into a list of actions.
I see.
Yeah, so I think this is superior to Voyager already, because if you ask GPT to generate code, there's a lot of chances of failure.
So how is it different from how we learn? It seems very, very similar.
I think what it does is that it matches semantic knowledge into action space. This whole LLM process matches what we know in some knowledge base into an action space. So the try and error part should come in the form of learning the knowledge base. Like if we have to build the knowledge base from scratch, then we potentially need to do some try and error.
I know, but I mean, just focusing on this feedback loop part, it's almost like how human learns, right?
Yeah, I like it a lot. Yeah, this is correct. So the way that the models use the feedback helps it to guide its actions in a sequential manner. So there's some like reinforcement learning in some sense, like if your original code doesn't work or original action space doesn't work, you take in feedback. It's like you tell your son like, your circle is not exactly a circle. You need to make it rounded at this part. Then you take this feedback and then maybe you draw a better circle. So it's quite cool. This iterative process of generation is it enables GPT or large language models to improve their answer to a limited extent, whereby the model is capable of understanding the errors. Like if the model is able to understand the error and like correct the error natively, this can work. But if the model cannot understand the error at all, then I mean the error should ideally be in text that has semantics, because semantic meaning is what drives the large language models. Yeah, so if you can have this kind of errors in terms of text, you can do potentially an error correcting loop to a limited extent to improve your code. So I mean, I tried the ARC challenge, it improved like twice the performance of my model. So I think this loop is quite helpful.
And so how is the error message generated? How does the critic knows what kind of mistake it's making? Like in this example, is too far. How does it know?
Oh, the critic is the world model actually. I mean, it's the environment actually. The environment will feedback. So in this case, this feedback, yes, you're right. This is the critic, but this critic is not learned at all. This is basically the environment gives back error messages. Yeah. So the critic.
Okay. So the assumption is that, it's similar to last time where the environment can directly give a error in terms of like semantics. I mean, like it knows, it can tell you like a high level idea what's the problem, what's the error. I think this part is very crucial. If we don't have a mechanism to do this, we cannot enable this feedback.
Indeed. So if you don't have a way to embody your error messages as text, this process won't really work. So what will happen is that you will just do this part. You will just do one cycle. You'll just do one pass. If you cannot do a feedback in terms of semantics,
then in this case, there's truly no learning. So
yes. Yeah. So I mean, it depends on what you mean by learning. Do you count memory as learning?
Yes, but even you have the memory, memory itself does not explicitly tell you what exactly is a mistake, right? You still need to do more primitive form of trial and error. But if the feedback give you the explicit problem, then you maybe you still do trial and error, but it's a much more efficient trial and error.
Yeah, so indeed, if you have an environment that can give you text feedback, it will help greatly. Yeah, so not all environments can do that, you're right. But I was thinking if you can code the API yourself, like the action list yourself, right? You can actually return error messages in your functions, like dig down, explore this. You can.
But saying this actually is not that. Actually, it's pretty doable if you.
It's doable if you know like what error messages to return. Like, or you can say that object not found, or this one not that Like, I mean, if you think of it in real life, if I want to drink a cup, then you can say cup object not found. You know, you can just like, assuming you have a Unity environment of real life, you see, then you can just say that, oh, this object cannot be found. Yeah, you
Okay.
can return error messages like that.
I guess the efficiency also depends on how explicit this feedback information is. If it's more explicit, means it's more helpful, means it gives more information, then you can improve much more efficiently.
Correct. I mean, I can imagine this happening in the robot system. Imagine you have your Zoom bot zooming around your house vacuuming, right? And then your Zoom bot comes inbuilt with some action list, like move towards XY coordinates, or like it could be like on vacuum, off vacuum. We could have that stuff like that. So imagine if it does the move towards XY, and then it like encounters an obstacle, then it cannot navigate through. Then you can say, you can return the error message path block.
Yeah. Instead of yeah, I mean, in this case, in the example you give, the path is blocked is a more informative feedback compared with like just say it's still too far, but it doesn't tell you why it's too far, because something is blocking your way.
Yeah, I mean, this can also be refined, I guess. Yeah, but right now this error message, I'm not sure whether this error message is done in the action functions here or is from the environment. So this one, because it's not open source, I'm not able to tell you, but I would say that you can code it inside the function. Yeah, so yeah, if you think about it, it's not that have to code basic actions and return error messages based on different contexts. Because like, let's say if you have a function like addition, add num1 and num2, you can then like, I mean, if you want to do a function like that, you can check if there are numbers, right? So if not, then you can return like not number error. I mean, assuming there's such an error, I mean, you can say you can return like inputs are not numbers. Then after that, you can also check if like num1 plus num2 is out of bounds. Then you return out of bounds error. Something like that. Yeah. So you could think of a function that you want to do addition. You can think of all, like if you are doing unit tests, you can think of all possible failure cases. And then like this kind of things can be fed as the feedback.
Yeah, but I think it still has different level of informativeness. I give you one example. For example, if you want to help, you want the language model. Oh wait, so maybe you continue first. We can discuss later.
Yeah. No worries. No, I'm almost done with the slides. You can continue. Yeah.
Okay. My example is, so for example, you want to teach the language model to solve a rather complicated problem, but it can't solve in one go. Then you ask it to break down this thought process, right? Then you try to give more detailed feedback for each of its reasoning step, as opposed to just say, okay, it's wrong. Maybe okay, you can even say, okay, it's numerical error, or it's your argument has some logical error, but it's definitely more informative if you break down into steps, say which steps has what kind of error. So that gives you like different level of like in the breakdown case of you agree like there's much more information to learn from, right? That's basically like you have a tutor. What makes a tutor good? Because he can feedback, give you very helpful information to help you learn, that kind of thing. So here, so I think it's a very interesting problem to see how do we improve this feedback mechanism, make it more informative, such that maybe the learner just receive one time feedback, you can already next time can already get the correct action.
Yeah, that's cool. Yeah, indeed. And actually, this feedback is based on the function also. So if the first function works, you won't get any feedback from this function. And maybe if the second function fails, then this comes to the feedback. So in some sense, it is like targeted feedback because it can probably tell you which action failed.
Okay. Another, I have another.
Actually, if you think about it, there's no need to see the open source code. You look over here, the feedback. The feedback is encompassed in the action. It's quite clear. Yeah, you look. This is like the action failed, and then the error message is here. So I think in this case, the error message might be self-crafted by the people who created this code.
Huh? You mean that this is a form of human feedback?
I mean, because when you design the function, you already know what are the failure cases, right? So you can just say what failed in the function.
So do they design a message in advance, or
Yeah, the message is in advance already. So like this target is too far. So this I believe is given by the creators of the paper.
okay? So another thought I have is you can see this is like a zero order optimization mechanism, right?
How so? Yeah.
It doesn't need any gradient.
Oh yes.
And you can learn from this, and it can be very, I can see it can be very efficient. So it's like very efficient zero order optimization. So you don't need, maybe it doesn't have the problem of like when you use RL like gradient based optimization like policy gradient or things like that. You don't have those the inherent issue with that kind of method. For example, not stable variance.
Yeah. I think this is indeed the future because gradient-based methods are very slow to learn. Large language models, if they can extract semantics well and you can just zero shot or few shot from them, wow, the possibilities are amazing. I believe if we ever achieve an AGI system, the backbone will be a large language model.
Because you can think of it as already doing optimization in the abstraction space, right? Or the latent space. If your feedback is good enough, means you already give it a like very good representation of the learning problem.
Yeah.
So that's why I said it's crucial to give very useful feedback. Yeah, that's why I think it's quite interesting.
Correct. Yeah. So with respect to your earlier point on whether or not it can learn through try and error, I think if it doesn't have the wiki database here, it probably will, if it doesn't have this, like because in terms of the goals that it receive, it has external info here. So assuming that it doesn't have external info, what would happen is that it will need to try out different things. So like maybe it will explore something. So I think what may be lacking if you want to do a try and error, you need to have a failure memory. So you need to, for each sub goal, list like stuff that failed. Then you feed this in terms of your memory. You feed this here so that you can do try and error. So like for humans also, like if we try out door A doesn't work, then we should go to door B, right? Then we should go to door C.
Yeah. But it's also possible to make use of this failure memory not in a brute force manner. So after you accumulate a certain amount of memory, you can do can learn like the way you learn from a mistake it's not just to try the next one, but you
can also compose your mistakes into some broad category.
Yeah.
You can do memory summarization. Yeah. I think this might be the missing link if you want to learn directly from Minecraft without any wiki at all. You need to record your failures. So actually, this was one of my discussion questions that I removed due to lack of time. I was asking like for skills decomposition, or like in this case for this memory, should we only record the successes? Because you see everyone here is trying to record the successes. You look here. If you look at this, where's my memory part? You only record the successes. Like we only record a successful memory. Then you can ask yourself, what about failures? I mean, are failures not important? In life, are failures important? They're quite important, right? It tells you what you probably shouldn't do, right? Like, I mean, I played games with my friends before, and then like I created games on my handphone. Then if I like let them play the game and they fail directly at the first level, they don't want to play anymore. So when I create games, I always make the first level winnable. All right. So this is the psychology, because people hate failures. The moment you fail one time, you're not going to play the game anymore. You're going to say, this game sucks. I'm not going to play it. Yeah. So similarly, in memory, I think failure memory is quite important, and all these architectures are missing it. So thanks for pointing this out. So yeah, I think this part about failures is actually useful for try and error, or not try and error, useful for explore exploit. Because if you have failed somewhere, you might want to explore other paths. So yeah, I think that's quite interesting. All right, anyone else? If not, I will just finish up the slides and we can go for discussion. Okay, maybe let's just do that since we're already starting the discussion. So this is the thoughts that I have. The architecture is more generic. primitive actions are very good because you can just use a baseline set of tasks. You can generate this big primitive functions already. No learning may restrict adaptability. Okay, but if your functions can be formed from primitive actions, like basically if all new tasks can be performed using that, then maybe you use memory can be enough already, which is the case of this paper. I like the idea of using LiDAR arrays because LiDAR arrays is much better than high dimensional 3D RGB input. If you ever use an agent with a 3D input, good luck. I think it's very hard to learn from it. Good luck. Yeah. So model answer is given to agent right now. So what does agent needs to do to find out purely through exploration? So we have answered this just now. So maybe we might need some memory of failure so that you can tune towards like what he hasn't tried before. All right. Any other thoughts before I go on to the conclusion? I mean the discussion.
How is LiDAR superior? Why is LiDAR superior to?
Oh, because LiDAR just tells you what the block is. So that's a forest 3 blocks away, or forest block coordinate like that. Yeah. So you don't have to decipher from, like, imagine if you have a Minecraft environment, it's a 3D environment. You need to decipher, okay, this is a tree. This is like the cliff. You know what I mean? Like, you need to sort of match this high dimensional input to be a tree in front of a cliff. And you know, you don't have the orientation at all. So it's very, very vague. But if you have like LiDAR arrays, you can say that, oh, there's this block here, there's a cliff block, coordinate is like something like that. Yeah. So it's much more specific and is able to do some form of vision understanding. In some sense, it's cheating a bit. It's able to do the vision understanding by telling it what block the LiDAR arrays land on. Yeah, so it's very low dimensional. Can you see that if you talk about forest block, cliff block, and the coordinates, it's very low dimensional. You only have the type of block and like the position. And maybe if you land on an opponent, you will have like zombie health is what, you know, that kind of stuff. Yeah. Okay, so I think I will just move to discussion. Okay, I actually have some slides on what I think an action space should be. So I will touch this next week, okay, because I want to go to discussion. So I was thinking that maybe we could have a hierarchical if something and then an action. Okay, so we can talk about this next time. Yeah, I'm trying to implement something like this for ARC also. spoilers. Okay, next week when I talk about ARC, we can talk more about this. This is like some code that you could come potentially generate in this format. All right, let's talk about questions to ponder now. All right, so this is where y'all can contribute. Okay, so first we talk about the first question, like in the Voyager paper for curriculum generation, how does the GPT know what tasks, okay, to create, okay, given this inventory, nearby entities, and equipment? Because right now, like for the Voyager paper, the curriculum is given directly by the teacher, by the curriculum generator. Okay, which they showed improves, like I think by 70% or what with the curriculum planner compared to like with a random curriculum. Yeah. So how does GPT know what are the next tasks to create? So I was thinking that maybe the list of tasks are already given. So it's a matter of matching the agent's abilities based on past successes and failures to the task. Yeah. So this is what I'm thinking. And yeah, so it's up to us whether or not like we buy that this is great. So Ray said this is from Wiki. Yeah, so that's correct. Maybe the list of tasks are already given from the wiki. So my understanding is the list of tasks are already given. So now, what about if you don't have the wiki? What if you don't have list of tasks? How will your automatic curriculum know what tasks to give? Do you like create your task yourself? Like if you have 3 iron blocks to say, oh, smelt 3 iron blocks together. You know. How does the curriculum generator know what is important? Like if you have a new environment that is not Minecraft, how do you know what are the 3141 tasks needed in the environment? I mean, who is to say what are the tasks? So this is the idea of in a new environment, how do we know what tasks do we need? Okay, this is more of a question. So a teacher will need to come up with it, but who teaches the teacher? Who teaches the teacher? Yeah. So this is I think a big problem. All right, if you want to have automatic curriculum learning, you need to have a curriculum to learn from. And who comes out with the curriculum? That will be defined based on like maybe, oh, I have a framework actually. I just thought of this. Maybe what could be done is like you have a list of, you have a series of playthroughs or like series of experiences. And then what will happen is that you will just find all subtasks based on this. Make them unique. So maybe you could have a task generator. You could ask the task generator to, based on this sequence of actions and states, come up with unique subtasks. Maybe you could do that. Yeah, so that may be one way to do it. I mean, the other way is, of course, researchers like to do diamond pickaxe, right? So we all focus on the diamond pickaxe pathway. Yeah, something like that. Yeah, so who came up with what are the viable goals and what are the worthwhile goals for research? Who comes up with them? The community, the people who craft the papers, and then they try to sell that this goal is very important to achieve. Yeah, so this is an open-ended question. Like, in order to train the agent with tasks and subtasks, it must be of some meaning to train from. And that some meaning needs to be defined externally. And you see, even this, find the list of subtasks, right? You need to have some form of condition over here. Someone needs to tell it what is meaningful. So of course, I cannot answer this right now, but you can imagine in order for it to be applied to any generic framework, we need to define all of this. Okay, then from then on, we can get the subtasks and tasks in order to train the method. Right, Ray said generic algo choose the top 10%. You meant generic or genetic? I think generic, right? Generic or genetic algo. Yeah, so yeah, maybe you could do based on tasks, we see what are the common tasks and what are the tasks that are easy for most people to do, what are the tasks that are hard for most people to do. And then based on that, you can draw like a pyramid of tasks. Like then you can say, oh, they're very, very smart people. These are the top 1% of tasks that only 1% of people can do, like play Go or play chess, then you can have different tasks. Now, why do you think in entire mankind, people think playing chess is the pinnacle of intelligence, right? Why? I mean, that's until Deep Blue trashed the leading chess player. But before that, everyone thought, oh, intelligence is playing chess. Have you thought about that? Yeah, and that's because the community defines that this is a difficult task. And we always like to say that everyone is special and, smart people are one step beyond the rest. And that's why intelligence became defined as only like maybe the very, very top few people can do that task. And so that's a very difficult task. But if you realize, like actually what 99% of people can do, like vision, stuff like vision and movement, everyone can do that. Why is it not an intelligent thing? Robots suck at doing that. Okay, I can say it like explicitly now. If you have a robot to make pizza or a robot to do bartendering or this, the chance of it failing is quite high because RL is very, very brittle. You change the environment a bit, maybe you don't know where to grab the bottle and the bottle crashes. I mean, there's this automatic coffee makers. I think in Singapore, one of them crashed. Yeah, so you can see that if you use robots for movement right now, it's really not good. Yeah, but with large language models and with ways to abstract vision into text, I think next year the robots will be much better. Okay, so hopefully we'll be part of that wave to make it happen. Yeah, so I can see it coming already. Reinforcement learning will be replaced by this kind of semantic based models. Okay, yeah, anything else before we move on to the next question?
I think it's very difficult to evaluate how you break down the task into subtasks, because if one point the link is not right, you can't finish the task, but it doesn't mean every subtask is wrong. So in a sense, you can have some of the subtasks correct, but you still can't complete the entire task because some point in the link is broken.
So you are saying that how does it know how to generate subtasks, right?
I'm saying it's hard to evaluate what subtask is good subtask.
Okay, so I think maybe one thing to phrase is like, if we evaluate a task into subtasks here, how do we know whether accomplishing the subtask can give you the main task, right? That's one way to view it. How do we know this can work? So like, is the subtask naturally decomposable from main task? So if it is, then it's quite easy to define a subtask, because it just means that it needs to be an order of complexity lower than the main task. But if you already know, like if your subtask completes, you get these items, and these items feed back into your top task, then you know that it can be decomposed like that. So
Okay, I see.
yeah, so I think it really depends on the task, because some tasks are more open-ended. Like if you have like GPT, some people have done something like Hustle GPT, like they ask GPT, make me money, like this task, how can you decompose this task? I mean, how do you decompose it? Make money is like have a company, work, there's so many different branches of tasks that could be formed from this task. So it's very, very hard to make subtasks from this. Okay, but for Minecraft, if you want to do like craft a diamond pickaxe. I mean, the crafting table is kind of obvious, right? You need to go from A to B to C to D. Yeah, so that's why they didn't have a feedback mechanism for subtasks. Why does AutoGPT fail at doing stuff like this? Okay, why? Because it's very hard to decompose this into compositional blocks like this. There's so many different pathways. Imagine if I have a diamond pickaxe, I can go to F, G, H, then how do I know that when I decompose it, I should decompose it in terms of B or F? Which one is better? What if there's multiple pathways that reach the same goal? Minecraft doesn't have this problem because Minecraft is quite linear in progression. But what if your task is very, very broad, very generic? You can also have a task called like create me a toy that makes me happy, or create me a game that makes me happy. So that is very, very generic, and that is probably not going to happen because that is too broad. Like, how do you decompose this into subtasks? What is happy? What is like? There's many things that can make you happy. Some things you do again, you may not be happy. Yeah. So stuff like that, when you cannot naturally decompose, I think there'll be a problem with the curriculum planner. But fortunately, for most real life tasks we're going to use the robot for, I think the task can be decomposed quite well. Like, for example, if you want the robot to make me a coffee, right? I mean, I think most people will agree that the steps for making a coffee is like this, right? Okay, I'm just going to imagine, all right? Find coffee powder, find cup, pour coffee powder. I mean, I'm talking about the instant coffee mix, okay? Not the atas slow drip. You need to. I'm talking about the instant coffee mix, okay? Pour coffee powder into cup, boil hot water. Actually, sounds quite long, right? Find boiler, find water heater, boil water, pour, wait for water to boil, pour water into cup, stir cup. Gosh, a robot that makes you a coffee is it's actually quite complicated. There's so many steps that needs to be done. Yeah, so I think that is but you can see that all the steps that needs to be done can be composed into a very natural hierarchy. Like coffee powder, this is the fine ingredients part. All right, and also the fine water heater part. So this is the finding part. Then we also have the action part, pour coffee, boil water, pour. So all these are the actions part. So this one is actually all in terms of a sequence. Like you need to do step A, then step B, then step C, then step D. So like make me a coffee could be decomposed into two parts. Actually, one part is find items, and then the next part could be use items. Yeah, I mean, you could do it in this way. Same as Minecraft. So you need to find the items first. You need to move to the ore to mine it. Then you can go back to the crafting table and craft it. Yeah, so you can actually decompose the task like that. Yeah, I think in real life tasks, I mean, unless you want to do very, very big tasks, in real life tasks, you can decompose them quite easily most of the time. Yeah, like all these kind of tasks are very big. So you probably shouldn't use this as tasks. Yeah. Any other thoughts? Yeah, sorry, I went on quite long on this. Yeah. Okay, so oh gosh, it's 2:07 already. Let's try to end this in 5 minutes. Okay, so the other thing is there a better way to represent skills other than through code? So I hope you all agree with me that code is not a great interface for skills because of the possible syntax errors. Like listing as a list of actions may be a better way. Yeah, I like the goals in the Minecraft method. But I think my method would be better. Like I was thinking of doing it like if condition, then action function, and if condition action function, because like sometimes you want to do a certain action, but it's conditional on certain things. Yeah, so it's either your if condition is inside the function itself, or your if condition is explicit outside here. So this could be inside this action function. You can, as one of the parameters for the action function, you can give a sequence of parameters such as, like, for example, you want to move towards XY, right? You can give like a restrictions. So the restrictions can be like only move, restriction could be like move y coordinate first before x. Yeah, you could do some restrictions here, then you don't need to do the if for the function. Yeah. Okay, Sam mentioned, I think it should use keyboard and mouse. I think the actions are giving a bit too much information back to GPT. Yeah, indeed. So they only do the high level planning. The low level planning part actually is not really done. Okay, it's already assumed as given. So we are skipping a lot of where RL is helpful, because RL, okay, doesn't really have semantics, you see. I mean, people are trying to infuse text-based semantics in Atari games, but for generic, most of RL, you don't have text-based grounding in the policy. All right, so that could help to match like a sequence of actions to a goal. Yeah, provided that your goal is well defined in the actions in the state space. Yeah. So yeah, I think in terms of like very, very fine motor skills, we haven't quite solved them yet. We still use RL to solve it. But then again, if you think about how a baby walks, they also take 1 year to walk. So maybe it is the case that RL is still needed for fine motor skills. But once we have mastered those motor skills to use them for higher level thinking or higher level planning, we can just use large language models. Yeah. Environment to RL, to language, to GPT planning, to RL. Sorry, Sam, are you talking about the way learning should be? Yeah, I mean, I'm thinking actually at the low level motor skills, it will be goal condition RL. Something like decision transformers, maybe. Yeah, and then at the high level, this can form already functional blocks. Functional goal-directed blocks. So it's like move towards goal location. Yeah, you could have something like that. And then at the high level, use language to zero shot learn for new contexts. Yeah, so I think this framework is very useful because this kind of framework helps the agent learn much faster. You don't have to do try and error anymore if you could match language semantics. That's what this kind of goes in the Minecraft and Voyager shows. Yeah, Ray, you mentioned RL has to feed in action and state in a structured way. Yeah, correct. So that's for current RL. Yeah, I mean, if you have RL using text-based inputs to map to an abstraction space, then maybe you don't have to have a structured way for state and action. You can use text-based goal conditioning, and then this goal text will map into some semantic space for the map into some embedding space for the RL agent. So I think that would be possible if you infuse like something like decision transformers. Yeah, I'm also doing something along that lines as well. Yeah, a lot of things I want to do, but I have not enough time to do it. Right now, I'm just focusing on up, but I'm trying to improve decision transformers. That's my other project. Yeah, because I think if you could do low level planning using action prediction. Maybe I just highlight over here. I believe action prediction is everything. So if you could, so this is the framework that I have. So like right now, decision transformers is just state, action, state, action, state. But if you have a goal over here, that goal state, and then you use this goal state, and then like action, another state, another action. Yeah, I always believe like if you were to just take this state here, and then basically given this state and given your goal state, you predict your next action here. I always believe that if you were to do that, like you predict the action that you need. So maybe here state 1, you predict action 1. State 2, you predict action 2. I always believe if you have this kind of format, all right, you can actually learn the abstraction spaces for goal, state, and actions. You might be asking me where's the reward. There's no need for reward because the reward is the goal. Yeah, so I also think that, I mean, language modeling might be able to help to get the abstraction space for the goal directly also. Yeah. So, okay, I mean, I'm not too sure whether like how this could be done. Okay, but this is my idea of improving decision transformers. So I call it decision transformers plus. Okay.
Yeah, I also think it kind of mitigate the alignment problem. Because if you directly use your goal and do away with sort reward,
yeah,
you won't have the alignment problem.
Right. Actually,
you didn't use any reward here, right?
I didn't what? Sorry, I have no reward here.
No, I mean this paper, they didn't use any reward.
Oh, you're talking about goals in the Minecraft, is it?
Yes.
Yeah, there's no reward. Yeah, and similar for my decision transformers plus. Yeah, I haven't actually written the paper yet, but this is an idea I have. I don't mind just giving it away because if it works, it is helpful for people to implement it also. This idea I have is to use decision transformer framework, and instead of reward, I have a goal conditioning here. Yeah, as the sequence, as start of the sequence. So yeah, so I think this kind of thing could help with the low level stuff, because low level stuff you still need to do actions, you still need to do state and action prediction, but at the high level you can just use language. So this,
if you think about it, the reward is totally to enable the gradient, right?
yeah.
And if you use semantic based zero order optimization, we don't need, that's why we don't need the reward. Everything is just condition.
But I'm saying even for low level, you don't need reward. For low level, as long as you can define your goal state.
Yeah, all the subtasks, right?
Yeah, so it's similar to the subtask thing here. If you're low level, you can say my subtask is to move my hand forward, my subtask to move my arm forward. You know, then you can use that as your goal, and then you don't even need a reward. Because if you think about it, why do people use rewards for reinforcement learning? It's because back then we don't have this kind of goal-directed learning. Back then, like we want to say, oh, if the robot reaches this square, then I give it a reward 1. All right, like reach this square here, I give it a reward 1. The robot starts here, and then if we can navigate to this square, I give it a reward 1. Okay, this was because back then we didn't really have this goal directed.
That's how you inform your goal to the agents. But
right.
Not just tell it you want it to go to that place, right?
Yeah, so back then, because architectures were much less complex, the reward was a scalar reward. You know, people don't have much memory to play around with, so they have to use scalars. So that was how reinforcement learning started, I believe. Richard Sutton book. But I think more and more increasingly, reinforcement learning is moving towards goal-directedness. It's because we have the memory space to encompass our goal inside the agent already. So I think the concept of reward would more or less kind of be outdated, because if you think about how they get the agent to walk using PPO, they bias the reward such that, oh, if the agent's body angle is tilted a bit more, then you penalize it. Body angle tilted a bit to the right, you penalize. It's a bit handcrafting, if you ask me. Like the reward is to like ensure that it walks in a way that we like. Yeah, but all this way of conditioning it can also be done through language. Yeah, I mean, you can just say we want to walk straight without the agent really going beyond a certain angle, something like that. Yeah, so that can be our goal. So the thing is, how do we represent this goal inside this low level space here from text? This is something that is difficult, because if you can represent, like from text, you can represent this goal space directly, you can do a lot of things. Yeah. So I mean, there's research trying to represent text as a goal in an embedding space. Yeah. So like, for example, those pick place environments in SECAN, there's a model that actually takes in text as a goal and conditions the policy based on that text. So I think all these are quite interesting developments. Yeah. But I still don't think reinforcement learning is correct. We shouldn't be learning from rewards. We should be just aligning to reach the goal. Yeah. Sorry, Sam, which paper are you talking about? The SECAN one, is it? Text to go. Sure. Yeah, I linked it in my second video. I'll go and find the link and send it to you later. Yeah. I just post it as the link in this video. Yeah. Okay. I think it's a very, very interesting discussion. So this part here, like how do we represent skills? I think this one really needs a lot more thought. All right. I think a sequence of actions is great. Okay, but the sequence of actions loses out a lot of conditional goals. All right, and the reason why this can work for Minecraft is because Minecraft doesn't need any conditional goals. Minecraft, you just need to find wood, make the crafting table, find iron, make the iron axe. Okay, sounds very I'm making Minecraft a bit too simple, but Minecraft is really quite linear. Your goals are quite linear, so your sequence of primitive actions are also very linear. Okay, you don't have very complex stuff like the arc challenge. If it's a square, you color it blue. If it's a rectangle, you color it red. So for those, you cannot just use primitive actions, because if you just say color red, okay, it's not going to cut out. You need some if condition there. Yeah, so I would say that the sequence of primitive actions should come with a condition. Right? Can all action spaces be mapped into code? No. Okay. In fact, code generation is not very good for GPT. All right. What are the pros and cons of denoting actions as code? Code is more expressive, of course. Yeah, but code also comes with a lot more errors. And because of the diverse generation, you are not guaranteed that the code would actually run. Yeah, so these are the problems with code. That's why I like those in the Minecraft better. Sequence of actions always runs. Okay, I mean, you will have no syntax error. The only syntax error, or the only error you have, is execution error, where you cannot execute your function because of some missing item or something like that. All right, last question before we end today. Should memory just be skills alone? Should there be memory at more levels? So right now, Voyager is memory in skills. Okay, goals in the Minecraft is memory in subgoals. Because the subgoals tell you like what are the list of actions. So should there be memory at more levels? Of course. There's actually some memory that could be done in goals as well. Like you can select goals that are more viable based on failures. Yeah. So there's memory in goals, memory in sub goals. There can even be, if you are talking about motor skills, you can have memory in motor skills also. So I believe memory is a hierarchical construct. You have memory at different levels. Right now, we are only exploring memory at the skill level or memory at the sub-goal level. But as what Sari said earlier, there's no feedback from the LLM Subgoal Planner to the goal setter. What if the sub-goals don't achieve the goals? What if it cannot be decomposed in a great way? Then you will need some feedback to tell it, okay, this sub-goal is good, this sub-goal is bad. Like if you were to ask an agent to try to like play Candy Crush, maybe. Yeah, in order to win the game of Candy Crush, you kind of need to have like different things you want to try. Maybe you have to break the biggest part first. Maybe you want to like form power-ups first. There are different goals you can do. But if let's say you break the biggest part and you realize it cannot work, then the next playthrough, you might want to do the power-ups first. Yeah, so something like that could, if your sub goals are not easily decomposable from your main goals, maybe at the goal level, you also want to have some memory to decide like how to split the sub goals based on what has worked and what hasn't. Yeah. Yeah. Any other thoughts on the last question? Okay, if not, I think it's a great discussion. And yeah, next week I should be talking more about what how I use this Voyager architecture to apply it on Arc. So I'm quite interested to share with you all, because the Arc challenge is a very interesting one. Okay, any last thoughts before I end? All right, thanks so much and see you all around. Bye.